Hey, this is Rorry, the founder of Perforated AI. I'm here to show you how to implement dendritic optimization into the official PyTorch MNIST example. In this walkthrough, we're going to have a timer at the bottom right here, just to show first-time users how fast and easy it can be. In fact, you'll see the timer pause occasionally because it's faster than I can talk. So let's get started. First, you of course will need to add your imports to get access to all the functions in our library. Then you have to find in the file where your model is defined. When I'm starting a new project with an open source repo, I often just do a search for model equals, and about 90% of the time, that takes you where you want to go. When you find your model definition, right after it is created, you will need to call our function initializePy. This sets up everything behind the scenes to turn your PyTorch modules into Perforated AI's Py modules, which enable dendrites to be added for optimization. Next is a setting that typically would get added at the end. It's called testing dendrite capacity. This tells our system to add dendrites every single epoch as a test to make sure there are no bugs and that your GPU is going to be able to handle the larger models before running a full training run. It defaults to true, so when you do want to run your full training, it must be set to false. After that, your optimizer and scheduler must be set up differently. The Perforated AI library has an object called the Py tracker. This keeps track of all the Py modules and how training is going so far. It also handles things with the optimizer and scheduler, so rather than instantiating them yourself, you pass the types and the parameters they would have used as a dictionary to the Py tracker with the functions you see here. Next is the add validation score function. This must be called after every validation cycle. It is the function that actually does the dendritic addition to your model and does so each time your validation scores plateau in improvement. When this happens and dendrites are added, the model that will get returned will be a different model. It has all of your original modules and parameters in the same places as before, but it also has all the dendritic parameters added. Because of this, restructured will return true as a flag that can inform you when you have to reinitialize your optimizer and scheduler, which can be done by copying the exact same dictionaries and setup optimizer function from above. Additionally, this function will return training complete. This returns true when the previously added dendrites did not ever improve the validation score. In this case, that final set of dendrites is deleted to not waste the parameters, your loop can be exited, and the final model can be returned. Lastly, in this specific example, the test function doesn't actually return the score we said we needed. So we need to set that value when the test function is called, and then go up to where the test function is defined and have it return this value at the end. And that's it. The MNIST example is now set up to implement dendritic optimization. Obviously, we're not going to have a recording of the full training being run, but we do have these two terminals open where we did that earlier. In the first terminal, you can see the baseline that gets 9918 out of 10,000 correct. In the second terminal, after dendritic optimization, the new number is 9934. Looking at mistakes, that means we eliminated 16 out of 82 total incorrect answers. That's a reduction in error of about 20%. Not bad for 57 seconds of coding.